method. For this first problem, I'm going to choose to use elimination. It's perfectly set up for it, right? You can see that I have on the left-hand side a negative 6x and a positive 6x in the two different equations. Again, our thinking with this method is I have things that are equal. I'm going to add things that are equal. So if you have equal things and you add equal things, you're going to get equal things. On the one side, I've got 22 plus 10, which is 32. Over on the left-hand side, I've got 3y plus y, which is 4y. And then I've also got the negative 6 times x plus 6 times x, which is 0. So that's gone. It was eliminated. Dividing both sides by 4, we see that y must be the value of 8. So we know what y is. Now we need to find x. What I'm going to do is use the second equation. The second equation right here, I'm going to use that to figure out what x is. I'm just going to go ahead and write that equation. It says, hey, 6 times the value of x plus y. We know that y is now 8 plus 8 is 22. If I grab my calculator, let's see, where is that at? There it is. Okay, I'm going to take the 22, calculator, 22, I'm going to subtract 8, that gives me 14, and I'm going to divide that by 6. When I do that, I get 2 2/3, and I'm going to ask my calculator to display this as a fraction, and it says it's 7/3. So I get that x is equal to 7/3. I think that's 14/6 also. So now that we know both x and y, we're ready to write our answer. This is the ordered pair. X is 7/3 and y is 8. And that point, 7/3 and 8, will work in both of those equations, right? It's the value that makes both of those true. All right, let's move on to part B. Part B, as I look at this equation, this is a great candidate for substitution. If I look at it, the top equation tells me I have this value of y, right? 4x plus 2 is equivalent to y. So what I can do is I can replace y in the second equation with this thing that's equivalent to it. So I'm going to rewrite the second equation. When I rewrite it using substitution, I'm going to get 2x plus 3 times y. Y is 4x plus 2, substituting in from the first equation, and that equals 34. Using the distributive property, we have the 2x plus, here we distribute, 3 times 4x is 12x, and 3 times 2 is plus 6, and that equals 34. I can combine these. 2x and 12x is 14 times x, plus 6 is 34. At this point, I go ahead and take the number 34 and I'll subtract 6. When we do that, we get 28. So this is 14x is 28. And now if we take both sides of that and divide by 14, we get that x is 2. So I know what x is, it's 2, but that's only part of the solution. What I'm going to do now is take that first equation, because it's set up perfectly to tell me what y is. It says y is going to be 4 times the value of x. We found that x was 2, and then plus an additional 2. So 4x plus 2, 4 times 2 is 8, plus 2, y is the number 10. So our solution here is the ordered pair where x is 2 and y is 10. All right, so that's question 1. Let's go on to a series of multiple choice questions. The first one says, which linear function? So remember, linear functions are those things that grow by adding the same value again and again. And we know the general form of a linear equation is y equals mx plus b. B is my y-intercept, and that's just added one time. What keeps being increased each time is we keep adding more m's. Every single time x goes up by one number, as x increases, we're adding an additional m. So for a function, a linear function, to be growing by 5, this value of m would have to be 5. So this is our answer. And another way we can look at that is if I go ahead and grab my calculator, here it is, and I could do a quick table where I type in 5 x plus the number 7, and I'm just going to have it go by 1 starting at 0. And when I do that, you can see, hey, 7 plus 5 is 12. 12 plus 12 plus 5 is 17. 17 plus 5 should be 22. 22 plus 5 should be 27. 32, 37. So you can see this indeed, 5x plus 7 is growing by 5, or adding 5 each time. The next question, question 3, says which exponential function has a multiplier of 6? So because it's exponential, I know my only two options would be A and B, right? Both C and D are linear, so those are out of the picture. For A, I am multiplying by 2. As x increases, right, it multiplies by an additional 2, and my 0th term is 6. For B, my 0th term is 4, and I'm multiplying by 6s. So B is my correct answer here. And if I was to look at that on the calculator, this would go from 4 to 24 to, I don't know what the next number is. 24 times another 6 would be more than 100. I'll just stop there. Next one, which values of x make the equation true? So I have this absolute value equation, and I know that this expression inside, right, this thing inside the 4x minus 2, because the absolute value of that is producing an answer of 30, I know that that 4x minus 2 is either equal to negative 30, or the 4x minus 2 is equal to positive 30. So think about the reasoning here. When I take the absolute value of something, right, when I take the absolute value of it, if I took the absolute value of negative 30, it would produce an answer of 30. If I took the absolute value of positive 30, it would also produce an answer of 30. So getting rid of the absolute value symbol requires breaking my equation up into two things I consider. Considering that this entire expression here is either a positive 30 or a negative 30. Now solving them is the exact same two steps, right? For this first one here, I'm going to take the number negative 30. I'm sorry, let me clear this. So I could take the negative 30 and divide or add 2 to that. So that's going to be 4x is negative 28. And then if I take the negative, the opposite of 28, and I divide it by 4, I should get negative 7. Yeah. Yeah. Negative 20. I'm sorry, I'm being distracted off screen here. Negative 28 divided by 4 is 7. 14, yeah. So this is x is negative 7. So I got a couple choices here, right? Negative 7. Yeah. Actually, so far, this is the only one. Let's see if the other one works. If I add 2 to both sides, I get that 4x would equal 32. And if I divide both sides by 4, I get that x would have to be 8. So I've got x is negative 7 or x is positive 8, which looks like choice C. And I can check both of those, right? If I plug 8 into that, 4 times 8 is 32. 32 minus 2 is 30. Absolute value of 30 is 30. If I plug negative 7 into that, right, if negative 7 was to go in here, that would be 4 times negative 7 would be negative 28. Negative 28 minus 2 more is negative 30. Absolute value of negative 30 is 30. So C definitely checks. The last one here, it says, which inequality is represented on the number line? I can see that this is an open boundary point, right? It's not shaded in. If it was shaded in, I would be using either the greater than or equal to or the less than or equal to symbol. But because I'm using this, it's either less than or greater than. And in this case, this is less than, right? All of my x's are smaller than that boundary. So this direction right here, they're all less than the boundary. So this is my choice, B, which is x's are less than 5. And if it was a filled in dot, it would be this one, x's are less than or equal to 5. And let's move on to page number 2, question 6. It says, for each function table, supply the missing values and the function rule. So this first one, we're told this one's linear. So that's nice. I don't have to figure out if this is linear or exponential. This is linear. And because I know that it's linear, I can just look at two adjacent cells, and I can see I'm going from 8 to 10, which is adding 2. So the rule for this function is add 2. And if I wanted to fill in more values for that, kind of a nice way to do that is just with the calculator, right? So I can look at this and I can say, hey, let's look at, well, you know, I'll put an 8 on the screen. I'll just say plus 2 and enter. And you can see it gives me the 10, and then it gives me the 12, and then it gives me, watch, 14, and then it gives me the 16, right? And I can check those going backwards. If I start with 16, if I'm going to go backwards, I would subtract 2. So that means the previous one should be 14, and then 13, and then 12 rather, and then 10, and then 8. And before that should be 6. Oh, and that's my 0th term. My 0th term is 6. So now I know both the 0th term, which is my y-intercept, and I also know the rate at which I'm growing. I'm growing by adding 2 each time. So the function rule would be 2x, I'm adding 2 each time, plus I'm starting at 6. So f of x equals 2x plus 6. This next one says it's a geometric relationship. So now I know that this is growing by multiplying by something. Question is, what am I multiplying by? Well, because I've got two values here, right? I'm multiplying by b, but I don't know what it is. So what I can do to figure it out is I can take 128 and divide it by the previous term, 64. And when I do that, I get, oh, this is easy too. This is b is 2. I'm multiplying by 2. So if I take 64, put it on the stack of my calculator, and I can say, oh, times by 2, it gives me 128. Then it gives me 256. 256, and then it gives me 512, right? Got it. And if I want to go backwards and fill this in, I can start with the 512, and what undoes multiplying by 2 is dividing by 2. So dividing by 2, I should get 256. Yep, 128, 64. The first term is 32, and the 0th term is 16. So I can see that my 0th term is 16, and I'm multiplying by 2, so the general form of a geometric explicit rule would be 16 times 2 raised to the x power. So that's the rule, and I can confirm that by looking at a table also, right? This is a previous problem, but if I was to just say, hey, 16 and then times 2 raised to the x power, take a look at what this gives me. Let me make it start at, I'll make it start at 0. So when I do this, it's like, okay, the 0th term is 16, and then you can see the 32, the 64, the 128, the 256. So all these show up here perfectly. So this is a nice confirmation that the table's behaving the way it should be. Yeah, because it's producing all the values that I observe in the table. All right, let's move on to question 7. 7 says simplify. One of the things I see in 7 is there is a 12 in the numerator and there's a 6 in the bottom, right? 6 in the denominator. So 12 over 6 is 2, right? So right off the bat, I'm just going to say, hey, this is going to be 2, and then there's an x cubed, over, now I can write a 1 if I want, right? 1 times x to the negative third, but that 1's actually not necessary, and I'll probably take it away in a minute. Okay, so now I have to deal with this negative exponent. Unfortunately, this is not x cubed over x cubed. It's x cubed over x to the negative third, right? So the technique we've discussed for dealing with negative exponents is to multiply this by x to the third power, x to the third power. So the reason why I selected that is I know when I multiply x to the third times x to the negative third, it will, I guess, neutralize that negative exponent, right? That literally will become x to the 0 power, which equals 1. So the only thing in the denominator right now is 1 times 1, right? In other words, I don't have to write the denominator because it's just 1. In my numerator, I've got 2, and you can see I've got 3 factors of x times an additional 3 factors of x, which is a total of 6 factors of x, so 2x to the 6th power. That is the answer for 7a. For 7b, oh, this is not, I don't think it's too bad, right? We've got 9 factors of x, so this is x to the negative 5th times x to the 9th. And a couple ways I can look at that. I can do the same thing that I did in the previous problem, where I make this go away by multiplying by x to the fifth in both my numerator and my denominator, x to the fifth. When I do that, same thing happens, right? I've just completely neutralized this x to the fifth, x to the negative fifth. That's the number 1. In my numerator now, I've got x to the 9th. In my denominator, I have x to the 5th. But look, 9 factors of x in the numerator, 5 factors of x in the denominator. That's just x to the negative 4th, or x to the positive 4th. So this is x to the 4th power. And I can see also, you know, negative 5 plus 6 is 1. 1 plus 3 is positive 4. Now, some of us are really struggling conceptually with what this is. And I encourage you to think about experiments you could do with your calculator to try and figure out what the heck this is, right? So I believe the answer is x to the 4th. And if I wanted to confirm that, I could look at something like, hey, let's say that x is the number 2. I'm just saying hypothetically, let's say that x is 2, right? This is my answer, but let's say x is 2. Well, I can look at what this equals, x to the negative 5th times x to the 6th times x to the 3rd, and I can compare that with what x to the 4th equals. These should be identical to each other, right? If they're not producing the same value, then I've simplified this incorrectly. And again, our calculators do such a great job of this task. Let's go ahead and bring up our the TI calculators. Oops, here it is. And I want to store a value of 2 in x. So you just press 2 and then say store that in x. Boom. Okay, right now my calculator thinks x is 2, which is what I want. And I want to compare x raised to the negative. Notice I'm hitting this button to get the negative 5th power. And I'm going to multiply that times x to the 6th power. And I'm going to multiply that by x to the 3rd power. I get this number. I get the number 16, right? I'll write a 16 right here. And I want to observe what x to the 4th is. Let's look. X to the 4th power is also 16, right? So the proof of this, right, is these laws of exponents we're using, right? We know that those are true, but good confirmation that I've applied the laws correctly is minimally it has to be the case that this original expression and my simplified version always have to produce the same outputs, and it's great confirmation that they are in this case. So this should be x to the 4th power. Let's move on here. It says write the inequality that is represented by each graph. So if I look at this graph, a couple points of interest. I know that I have a y-intercept that's at -2. And if I look at the slope pattern, it looks like the slope is down 2 and then over 1, 2, 3. So if this was going to be an equation, right, it would be -2/3 x, and then my y-intercept's at -2. But it's not an equation, it's an inequality. So I'm talking about what values of y work here. Well, the values of y that work are the ones that are below that boundary or equal to the boundary. And the reason why I say or equal to the boundary is because this boundary is solid. So because it's a solid boundary, it includes those points. So we'll just go ahead and say, hey, y's are those things that are less than the boundary or equal to the boundary. And that's what we're looking at, right? This is all the shaded region down here is represented by that one, that inequality. The next one, you can see I've got a dashed boundary, right? So I'm going to be using the not or equals to one, just the strictly greater than, strictly less than. My y-intercept occurs at 1, and my slope pattern is up 3, 1, 2, 3, and over 1. So I can see that my boundary line, this dashed line, is, what is it, 3x? 3x plus 1. And I can see that my y values are those things that are above that boundary. My y's are greater than the boundary. They can't be equal to the boundary because it's a dashed line, but y's are greater than the boundary. That's fabulous. Let's move on to question number 9. 9 presents us with 2 equations. It says solve each equation and also include a check for your solution. So for this first equation, I'm going to go ahead and clear the fractions by multiplying both sides of it by 10. Yes, I know this is a proportion. I know there's other tools that I have, but I just like sticking to this one thing that I know works. So I'm multiplying both sides of this by 10. That means that on the left-hand side and on the right-hand side, I'm going to be placing a factor of 10. So if I want to write this, I could say, 10 times the quantity of 3x minus 3 all over 5 equals 10 times the quantity of 15 plus 3x all over 10. So some wonderful things happen, right? One of the things that I see happening is on the left-hand side, this is a giant 1, right? 10 over 10. They're factors, right? It's multiplication, 10 times something over 10. So that right-hand side is just going to become 15 plus 3x. Over on the left-hand side, 10 divided by 5 is 2, right? So I can simplify that. 10 fifths is 2. This is equivalent to 2 times the quantity of 3x minus 3, which is 6 times x minus 6, and that is 15 plus 3x. If I take away 3x from each side, this would become 3x over here. And on the other side, when I take away the 3x, I've got just 15. Now I'll add 6, so 3x is 21, and then finally I'll divide both sides by 3. X is the number 7, so x is 7. Now, what does a check look like? Well, what we do is we believe we know what x is, and we just need to make sure that it makes both the left and right hand side the same. So I go ahead and say, hey, 7, store that in x, so I've got what I think x is. On the one side, I have a fraction that is 3 times x minus 3. I'm dividing that whole thing by 5. And that produces 18 fifths. Now, I'm correct if the other side produces 18 fifths as well, so let's check it. We've got a fraction. I'm going to enter 15 plus 3x. 15 plus 3x. And I'm going to divide this side by 10. And when I do, I get also 18 fifths. So when it says include a check here, it's something like this, as minimal as this. Hey, when I plug in the value, I can see that both sides become 18 fifths. And because 18 fifths is equal to 18 fifths, 7 is truly the value of x that makes this equation true. All right, then part B looks like a nice opportunity to use the simplest form of the distributive property. So I'm just going to write this as x minus 15. On the other side, I will have 12x plus 3 times 7 is 21 minus 14. Let's see, 21 minus 14, I believe that's 7. So this is going to become 12x plus 7. That's not writing well, plus 7. On the other side, I've got x minus 15. I think I'm going to go ahead and I'm going to subtract an x from both sides. So this will become negative 15 is equal to 11x plus 7. What did I do? I subtracted a single value of x from both the left and the right. And now I'm going to subtract 7 from both sides. So I've negative 15 minus 7, I believe is going to be negative 22, and that will equal 11x. And now if I divide both sides by 11, negative 22 divided by 11 is going to give me what x is, which is, hey, negative 2. So again, that's what I believe x is. Let's perform a check and verify that it works. Where's that calculator at? There we go. So I'm going to go ahead and store x as negative 2. So here's my negative 2, right? The opposite of 2. Store that in x. Got it. And now let's look at the left-hand side. The left-hand side is x minus 15. Oh my gosh, I could do that. Negative 17. On the other side, you can see I've got 3 times the quantity, 4x plus 7. And then let's decrease that by 14. Oh, not 17. By 14. There we go. And when I enter that, it gives me also negative 17. So when x is negative 2, right, negative 2, both the left-hand side and the right-hand side of this equation become negative 17. And because negative 17 is clearly equal to itself, this checks, right? So here's my solution, and there's my verification that is indeed the solution. Next, question 10 says, carefully graph the system of inequalities, and then also, it says graph, and then carefully shade the solution region. All right, let's start with this. First of all, that first inequality is y's are less than or equal to this boundary. The boundary has a y-intercept at positive 4, and it has a slope pattern of down 1 over 3, like that, down 1 over 3, down 1 over 3, down 1 over 3. So we're looking at something roughly like this. There we go. The other one has a, what else can we say about that? That is a, clearly that is a solid line. It's solid because it's got the or equals to it. And also it says that y's are less than that. So I'm just going to put an arrow here. I'm shading below this orange line. I'm going to be shading below that one. Let's take a look at the other boundary. The other boundary has a y-intercept at negative 3. And it has a slope pattern of up 3, up 1, 2, 3 over 1. There we go. So this one, I need a, let's see, can I change this? It's not a dashed line. Oh, I'm going to change this to a dashed line. That's too, you don't need to see this. Let's see. This should look good. So down 1, 2, 3, back 1. So roughly this. Yeah. Not so great. Can I extend it? Okay. There we go. There we go. So it's a dashed line because I'm indicating that the points on that line are not solutions, because this says y's are strictly greater than that boundary. And greater than that means I would be shading above the green line, above the green line. Well, it turns out the places that are above the green line and below the orange line are right in here, right? These are the points that are solutions to both. So my solution region are all the points that live in here. Any xy point, I could select any one of these, would make both of the inequalities true. That's the solution region. All right, let's see next, 11. Ooh. Write an exponential curve in the form y equals ab to the x that passes through these 2 points, 398 and 4686. So one thing about these is every single time I see them, it's easier for me to look at these in terms of a table. So I'm going to look at an xy table. I do not know the 0th term. I don't know the first. I don't even know the second term. But I do know the third term. And quite fortunately, I know the 4th term, which is adjacent to it. The 4th term is 686. The third term is 98. Now, this is an exponential curve, right, in this format. So, hey, I can figure out what my multiplier is because these numbers are going to live right next to each other. So to do that, I would grab my calculator and I'll just take the bottom term there, 686, and divide it by the previous term, 98. What that tells me is that it appears as I go down this list, I am multiplying. I'm multiplying by the number 7, right? Each time I go down, I'm multiplying by 7. That means that B, my multiplier, right, B is the number 7. The thing I don't know is I don't know what my 0th term is, but I can get it, right? Because if I take 686, whoops, wrong calculator, 686, and I divide that by 7, right, I can go backwards. So 686 becomes 98, becomes, I meant to do this. You hit 686, put it on the stack, then you say divide by 7. Here's the magic. 686 becomes 98, becomes 14. This is the number 14. Becomes 2. And if I divide that by 7, I'm going to get 2 7ths. Yeah. If I kick that into a fraction, it's 2 7ths. 2 7ths. Not exactly pretty, but I do know everything I need to know. I know that my 0th term is the fraction 2 7ths, and I also know that I'm multiplying by 7. So it looks like I can write the answer as y is equal to 2 7ths is my 0th term times a bunch of 7s raised to the x power, right? How many? It depends on which one you want. Now, just as a confirmation for this before I move on, yes, I'm going to go to the table. I'm going to clear this table, and I'm going to enter this new one, clear. I'm going to say y is equal to 2/7. I'll go 2/7. There's that fraction, times 7 raised to the x power. And if I take a look at this starting at 0 and stepping by 1, I can see, there we go. I've got 2/7, and then it goes to a 2, and then a 14, and then it goes to 98, and then it goes to 686. So this is exactly the exponential curve that would do that. Last page says solve the following inequalities, sketch your solutions on the area provided. Let's use a calculator. Why? Because I'm tired. I'll start with 57, and I will subtract 7. What am I doing? Let me quit this. I take 57, and I'm going to subtract 7. Roberts, are you serious? That's 50. Oh yeah, you make a good point. So this is 10x is greater than 50. If I divide both sides by 10, I get x is greater than 5. Okay. So, you know, just in terms of like finding the boundary and then testing, you can see I am tired because I'm not finding the boundary and testing. I'm just doing this here. So my boundary is at 5, and it says that my x's are those things that are larger than the 5. So this should be the direction of these solutions. So if I was to plug 5 in there, it wouldn't work because it would make them equal. But if I plug anything bigger than 5 in, it would work. So for example, if x was 10, this would become 10 times 10, or it would become 107. 107 is clearly greater than 57. So that's the right direction. That is. Let's look at the last one here, B. So for B, let me get rid of this calculator. It's right in the way. For B, I'm going to add 10 to both sides so that I get that 5x is less than or equal to 35, right? So yeah, I can add 10 to both sides of an equality and not change the direction. We've investigated the conditions in which the truth of an inequality statement changes if you multiply by a negative or divide by a negative number. We've also looked at it in terms of boundaries too. So now if I just take the 35 and I divide by 5, guess what? 5 times 7 is 35. So I think that my boundary is going to be 7, right? And it says x's are going to be less than or equal to that boundary. So at 7, at the number 7, I'm going to now use a solid boundary. I'm drawing that in, and it's going to be everything that is smaller than that. So everything this direction. There we go. All of those are solutions to this original inequality with just the single variable x. Right, and then finally, last question says, reflect this triangle across the y-axis to produce a new triangle, and then tell me where the coordinates for this new triangle are. So we, of course, have our x-axis and we have our y-axis, and I'm asked to reflect across y. So the y-axis is essentially serving as a mirror in this case, right? And when I reflect across it, everything on the other side is equal distance from it. So a -7 is going to become a +7 for my A. So this would be the location of A prime. -4 is going to become a +4 for C. This is going to be C prime. And -10 is going to go to +10, and B was up at 3. So my y values aren't changing at all. This is going to be B prime. What is changing are my the x values. The x values are actually just becoming the opposite of what they were. So I guess I can go ahead and I guess I'll just connect these. Oh, I didn't want that to be a dotted line. Oh well, I got a dotted line. I'll deal with it. There we go. So we've done this reflection here. The last part is, okay, what are the coordinates of the images? Well, A is at -7, 9, -7, 9. B prime, A, that was A prime. B prime rather. B prime is at 10, 3. Right, x is 10, y is 3, and C is at 4, 1. C prime, rather, is it 4, 1? All right, that looks like that's it. That's the last question. So, hey, good job. I know a lot of you have been trying your hardest to show some improvement, so keep it up. We've got a few more opportunities before the end of this school year, so let's finish strong. This is Mr. Roberts. I'll talk to you later.